So once again, my name is Wilfred Justin. I am from Amazon Web Services. I think today we have James Hancock, founder and CEO of Parasanti. And I think we have Rajesh, CEO and founder of Edge Tensor. And we have JD. The format of this presentation is going to be, I think the whole session is for 60 minutes. And for probably 25 minutes, I'm going to talk about a couple of things, including why people do machine learning at the edge, a couple of use cases that dictates doing inference at the edge. And for those kind of use cases where you need to do inference at the edge, how you can leverage AWS services. And probably we can spend a few minutes on how we can optimize the inference process at the edge. And maybe if time permits, we can talk about a couple of design patterns where absolutely you have to do, based on the data that you collect from the devices and IoT devices, you have to analyze that and probably run some kind of machine learning, but the device is so constrained, you cannot even run inference on those devices. So what we do that, how do we handle those kind of scenarios? We'll spend a couple of minutes and probably we'll straight away jump into the panel discussion. Does it sound good? So if it sounds good, I'll get started. So you can see my screen. I assume that you can see my screen. To the left or to the cloud inference is something that we all know about, right? You could collect lots and lots of data from IoT devices, or it could be from anything, right? App servers, web servers, hardware, and a lot of devices. On that cloud inference, and cloud computing platform like AWS is awesome for that because it provides a lot of big data services using which you can ingest data and process data both in real time as well as in batch mode. So it would let you build some kind of data lake easily, on top of which you can build and train and tune a model, and then the model can start generating predictions. And we all get it, and we all know how to leverage the cloud. But we are going to focus, this presentation is going to focus on the edge inference, where you have to do the same thing, but probably here you're collecting lots and lots of information from the devices, sensor data, but you cannot afford to make an API call to the cloud, and you have to run inference at the edge. So based on that inference, you can take a lot of, how do I put it? Well-informed decisions, which could be for operational efficiency, or it could be for predictive maintenance, and so on and so forth. And we're going to focus our presentation and discussion on the right side, which is edge inference. So to begin with, let's talk about a couple of reasons why customers and partners have to do kind of analysis or machine learning or inference at the edge. It's a no-brainer, you all get it, but I'll quickly go through a couple of use cases, right? One of the reasons could be privacy and compliance. Think about a hospital environment, right? Or a medical equipment where it could be an ICU where lots and lots of devices are connected, and based on the data, based on the threshold, you have to inform a doctor, or you have to do a couple of things. Mainly here, it could be because of privacy. You have to make those kind of analysis and decision on site, and you cannot send data back to the cloud. But the real reason, most of the time, the real reasons are network latency and bandwidth. And as we all know, there are applications which has to run probably in a zero bandwidth environment, and those applications demand instantaneous inference. And the obvious example that I can give is self-driving cars. You cannot just afford to collect data from all kinds of sensors and make an API call to the cloud to make the decision on how to steer the car. That would be disastrous. So you get it, right? We cannot afford to have round trip time, and those kind of scenarios dictates using inference and machine learning at the edge. Cost could also be a factor for extreme use cases, right? And this one, I got it from Toyota Connected Car, and Toyota Connected Car is one of our customers, and they build on AWS for the backend solutions, as well as for the machine learning. They use lots of services from AWS, including deep lens. So here, as you can see, a connected car has literally hundreds and hundreds of sensors. And for one particular use case where they wanted to use deep lens to provide safe driving application, right? So if the driver is distracted, it should alert and should take some corrective action. So for that, they did a small case study, and as you can see, based on that particular case study, a person was driving the car for 48 minutes. And based on that, they were collecting 7.2 million data points per connected vehicle. How do they do that? Because they had to connect 500 plus unique data points every 200 milliseconds. And if you do the math, it comes around 7.2 million data points per connected device. So extrapolating it, they had a fleet of 7.5 million connected vehicles. So even they did the math, and they said even if they're capturing 1 minute of high quality, high definition video per vehicle, the cost of uploading the data, for analysis, regular analysis or machine learning pattern detection in the cloud, the cost of uploading would be billions of dollars. Of course, the point I'm trying to make is still you can do deep analytics in the cloud, and instead of sending all the data using the network bandwidth, you could use Snowmobile family of products to send it, right? But you get the point. There are a couple of use cases where mainly because of latency and bandwidth, it doesn't make sense to make an API call to the cloud, and you have to do your machine learning inference at the edge. So for those kind of scenarios, I'm going to quickly go through a couple of services, and then we can open it up for the panel discussion. So again, a small disclaimer, I'm not going to talk about different services. I hope the audience who are listening in, we had multiple sessions on machine learning, outposts, local zones, and Snowmobile, a family of products. So I'm just going to focus on architecture patterns and design patterns and a couple of use cases, and talk about how we can leverage the services for implementing machine learning at the edge. So obviously, the first service that comes to my mind is Amazon Sagemaker. And Amazon Sagemaker is a higher level, fully managed service. And the whole intent of Amazon Sagemaker is to help you build, train, tune, and deploy custom machine learning models. It makes the process much easier and simpler. That is Amazon Sagemaker. So when you're using Amazon Sagemaker for machine learning, it comes with a lot of algorithms. It comes with 17 plus algorithms that is part of Sagemaker. But you know what? You can also bring your own algorithm. So you can use Amazon Sagemaker to abstract a lot of infrastructure work and expedite the process of building the machine learning model. On the other hand, you may not want to use a high-level service for whatever reason. In those cases, you can use our Amazon Web Services deep learning armies. And as you know, we are kind of framework agnostic. We want to provide flexibility to our customers and partners, so we support multiple frameworks. So we provide a lot of deep learning armies based on TensorFlow, Keras, Onyx, MXNet, and so on and so forth. So depending on the use case, you can build your machine learning model using that. And of course, you can deploy it using Amazon Cloud Compute, right? EC2 instances. I don't have time to digress on that. We have a lot of instance types, which includes compute optimized, storage optimized. And when it comes to machine learning, you have really powerful instances like P3DNs, which has 100 megabits per second of networking. So that's the point. But so Sagemaker, you have to start with Sagemaker because you have to build the model. But we are talking about edge computing. We are going to focus on edge. So I'm going to just mention AWS IoT. And probably you would have learned a lot, and you would have gone deeper in a couple of sessions that happened in the last couple of days. So I just want to briefly mention a couple of services. So under AWS IoT umbrella, we have things for analytics. This is where we can talk about site-wise, we can talk about analytics, which means that, think about it, you have billions of devices, and you want to, for industrial application, and you want to quickly collect data from those devices so that you can do some kind of analysis, and you can make well-informed, intelligent decisions based on that. For that, you can use IoT site-wise. How it works, we can digress if time permits. So that is site-wise, analytics, graphs, and so on. On the right-hand side, when it comes to device software, how we are going to provision devices, how we are going to push software into your device and make sure that the devices are updated to the current software and current operating system and so on. And think about it, right? If we have 1,000 devices, that is fine. But if we have a lot of customers that we deal with, literally have hundreds and thousands of devices or millions of devices. So if you're going to do it manually, push software and take care of the software updates and so on, it's going to be a painful process because of intermittent connections and so on and so forth. So leave that to a service called AWS IoT Greengrass, and Greengrass will take care of pushing the device and pushing the software to the device and so on. I just want you to understand that, because that's what we're going to focus when I talk about inference of the edge. Lastly, let's take IoT Core, and probably during our panel discussion, we can talk about security and compliance. So when you collect data from the devices, probably devices have to exchange information. How do they talk with each other? How do you take care of data at rest security and data and transit security, right? How do you do encryption? How do you do mutual authentication? Say, for example, you might be using certificates, you might be using encryption, using keys. So those devices have to be provisioned with those certificates and keys, and an AWS IoT Core comes handy for that, right? So those are the couple of services you have to remember. So coming back to our topic, deploying and predicting with AWS Greengrass. So in our case, in both Edge Tensor as well as the Parasanti solution, we are going to talk about, probably you're using a lot of devices, but how you're going to deploy the machine learning model into that devices. The first step is, as I mentioned, start with Amazon Sagemaker, build your model, train your model, tune your model, and then probably you can write an AWS Lambda function for the inference, and then use AWS Greengrass to push the model as well as the Lambda function into the device, so that the device can start generating inferences and it can take local actions on the device, right? So that is a simple data flow. And probably depending on if you want to have extracted intelligence to the cloud, you might want to sync back vital pieces of information, including data, back to the cloud once a week or once a month or once a day, depending on the use case and depending on the connectivity, right? So again, how do you do that when you're talking about machine learning at the inference? Train a model in Amazon SageMaker, write an AWS Lambda function for prediction. So add both as resources, Lambda function as well as the trained and tuned model into your AWS Greengrass group, and let AWS Greengrass handle all the deployments and updates. And again, because of the time constraint, I cannot digress to AWS Greengrass, but you can define what are known as groups. A group could be one device, or it could be thousands of devices, or it could be one main device and a group of satellite devices that connects with the main device. So you can configure the group in whatever way it makes sense, and you can use Greengrass to push the software to that based on the groups, resources that is defined in your AWS Greengrass group. So obviously, in order to do this, the requirements are your devices should be powerful enough to run AWS Greengrass, and we can talk about it, right? I think most of the devices like Raspberry Pi, and we'll talk about DeepLens and a couple of others, they're all AWS Greengrass compatible. So when you're doing the panel discussions, you guys can throw some light on what kind of devices that you use and what are the challenges that we have with that. But requirements perspective, it should have Greengrass. You should have powerful enough to run Greengrass. And obviously, as I mentioned, right, for mutual authentication and encryption, you have to have certificates and keys that should be provisioned by your IoT Core. And probably you can read what is there on the left side, right? It is best when the same programming model is in the cloud and the edge, meaning that you're building the model, you're simulating what is required in the edge in the cloud, and you're just pushing the trained and tuned model to the device. So I'm going to briefly touch on DeepLens. And why do I do that? Because we have a lot of partners who provide video security solutions like Edge Tensor. And my team is working with at least 2 or 3 partners who are building solutions based on DeepLens as we speak. So it is custom built for deep learning. It supports many frameworks, including MXNet and TensorFlow. And it is tightly integrated with SageMaker. And it is tightly integrated with SageMaker Neo, which I'm going to talk in a couple of minutes. So that is DeepLens. For example, I think Toyota connected car built an entire driver safety application based on DeepLens. So there are a lot of other things that we're doing when it comes to device detection, gun control, and so on and so forth. So again, the concept is not different. In this case, the device is DeepLens. And if you recall what I mentioned, you're going to use green grass and you're going to push the train model. And we talked about the lambda function for inference into the device. And then the deep lens has a camera. As I showed you, it can take the input, and based on the model, it can generate inferences and so on output. A couple of scenarios that we actually use deep lens for a lot of sessions, and it detects a lot of people, as you can see, right? But the point here is ImageNet, Caffe, and TensorFlow are supported, and it is tightly integrated with Amazon Sagemaker and Sagemaker Neo. So with that, I hope we can ask questions, but since it is forum, it's a virtual thing, I'm going to proceed. I'm going to give a small pause, and then let's proceed. So the next topic is optimizing performance for inference at the edge. I am really interested in this topic, and I'm really keen to know more about how you're dealing with this in our panel discussion. But the point here is the devices, since we are running machine learning at the edge, the devices are not really powerful. They're not like P3DNs or C5s, right? They have a lot of constraints that include computational power, memory power, power consumption, storage, so on and so forth. So if you think about deep learning and machine learning, when you're building a model, and if you want the model to generate predictions with highest accuracy, the models are really large, right? And there are multiple reasons. Once again, we don't have time. The models become really large because the deep learning neural network starts having multiple layers, and it has to do complicated computational tasks. It has to process multiple parameters, and it has to do a lot of complicated arithmetic operations, including 32-bit floating arithmetic, right? So the model becomes really heavy, and when you're trying to deploy that heavy model, large model on a device, which has a lot of constraints, it kind of defeats the purpose, and the performance deteriorates pretty badly, right? And probably you may not be able to use it. So once you have the model, you have to make it smaller and faster for the devices that you're deploying. And there are a number of techniques. This is where I want to really spend a couple of minutes and to start you guys thinking, and we can dive deep into it during our panel discussion, right? So how do we achieve that? People are doing that today as we speak. But again, it is really complicated, right? You have to do code optimization. You have to do you have to reduce the weights, as I told, right? From a larger weights to smaller weights. And there are a lot of techniques like quantization, mixed mode training, and so on. There are other techniques like pruning and compression. The point I'm trying to make is, yes, it can be done, but in order to do that, you have to have not only people who have a lot of expertise and experience in machine learning. Now suddenly you need those developers to have in-depth knowledge on the framework on which they are building. And also they have to know deep knowledge on the devices that they are deploying, because the in-device, the target architecture might be based on Intel, it could be based on ARM processor, it could be based on NVIDIA. So since you have to optimize it for the end architecture, you have to have a lot of expertise in multiple fields, and quickly it becomes really complicated. Say, for example, code optimization. One quick example I want to give. If you're using some kind of device like deep lens, and if you're doing some kind of video detection and analysis using deep lens, using TensorFlow, you're not going to deploy that TensorFlow framework into deep lens, because deep lens uses Intel Inference Engine. So you're going to convert that format into an Intel Inference Engine format so that it runs much faster and efficient, right? And there are a lot of open source tools like NNPAC. Similarly, when it comes to a larger model, how do you reduce the size of the model? As I said, in any kind of deep learning neural networks, the weights and activation are 32 bits. And by converting the 32-bit weights into 16 or 8, you could save a lot on both storage, processing power, and even the power consumption, because the 32-bit floating arithmetic are very expensive. Once you convert into 16 or 8, it becomes smaller. The model becomes smaller. It is more efficient, and hence it consumes lesser power, right? So those are the things you could do, and a lot of frameworks do support it. But the next challenge is, when you're doing that, right? When you're doing, number one, the first challenge is you have to do a lot of work manually to optimize your model for the architecture. Second, once you're dependent on a framework, the model you have built tuned and trained is kind of wedded with the framework, meaning that if you're building a model using TensorFlow, and if you want to deploy the model at the edge device, you need the entire framework on the edge device. The best example I can give is, say, for example, if you're building a C++ application on Visual Studio, or if you're building a Java application on Eclipse, when it's time for running those applications, imagine you have to take the entire Eclipse or Visual Studio into your edge device. That is not practical because the device doesn't have a lot of space, right? So those are the two problems that we have. One is you have to do a lot of optimization. Second, if you're building a model based on the framework, it is kind of wedded to the framework. So that's where you can leverage one of the services from AWS called AWS SageMaker Neo. So Amazon SageMaker Neo is part of Amazon SageMaker, and this exactly addresses the two issues that I mentioned, right? We're not going to spend a lot of time on this, but a lot of time on many things, but I just want to spend a few minutes on this one, right? So the first step, what it does is, it takes the machine learning model, which is being built using a framework like TensorFlow or MXNet, and it compiles it into a framework agnostic intermediary format so that you don't need the framework at the edge device. So you have converted into one particular intermediary format, which is agnostic. So all you can do is deploy that. But in order to, since it is done by SageMaker Neo, you don't need the framework, but you need the Neo runtime at the devices. But comparing the framework, if the framework takes gigabytes of space, the Neo runtime that supports most of the devices out there takes only megabytes. So right there, you save 100x on space, right? That is space optimization. That is the first thing that we do. Second, we work really closely with multiple device manufacturers, meaning multiple device manufacturers whose architecture is based on different kinds of processors, like NVIDIA to Intel to ARM and Xilinx. And we keep expanding our relationship with multiple vendors. And the reason is, first, we have solved that issue, right? The wedded model to the framework has been removed, and we are converting the model into a common format. That is number one. Number two, the second problem that I was talking about was optimization. And it's a deep topic, and it needs a lot of expertise. But from a very high level, once we do that common model, common format, we do a lot of things. One, we do compute optimization. This is where we might be doing quantization. We might be doing pruning, right? So we are detecting patterns in the model structure to reduce the execution time, which is the computation time. And also, depending on how the tensors flows between different layers within the convolution in the deep neural network, we detect patterns there in the shape of the input so that we can optimize on memory consumption. So we are doing compute optimization, we are doing memory optimization, and finally, we want to leverage the hardware architecture. So we pass through a low-level compiler as a final stage to generate a machine learning model that would represent the target architecture, and it could be based on Intel, it could be based on ARM, and we try to leverage the hardware vendors' libraries. So if you think about it, probably most of you guys are doing it already. It is a convoluted process, but typically we do a lot of demos and hands-on workshops on this. So when you're doing SageMaker Neo, literally it takes, all you have to do is upload your model, define what framework you have built, and you have to say what is your target architecture, and the magic is done by a SageMaker Neo behind the scenes. So the point is, it drastically reduces your time to market and time to production, and not only that, you gain like 2x better performance on the end devices. So that is SageMaker Neo. And finally, I just want to cover a couple of design patterns before we start the panel discussion. So we talked about a lot of services that you could leverage, but there might be scenarios where local inference is not even possible because the device is so limited in terms of memory and processing power. You cannot even do inference at the device, which means that you cannot push the model, you cannot push the Lambda function. So what happens in those kind of scenarios? There are two things, right? Those kind of devices, most of the devices support HTTPS, or it can support MQTT protocol, right? Let's take device that can support HTTPS. I'm going to go quickly. Yep. So same here, right? You train a model using Sagemaker, and as you know, probably most of you have used Sagemaker, and deploy to a prediction endpoint. You can have Sagemaker endpoint and you can deploy it. And at that point, it becomes like any other AWS service, right? You have a model, it has an endpoint. You have to make, you can invoke an endpoint using an API. So at that point, what it does is the model is already trained, it is deployed in the cloud, and it has an endpoint. The device, what it does is it collects all the information because of using IoT and other protocols, it collects information. But when it wants to generate predictions, or when it wants to do some kind of analysis based on the data it has collected, it simply makes a HTTPS post call to the endpoint. It sends the input and it gets the output. So again, I'm going to skip all the details, but you know that, right? Network should be available and devices must support HTTP. The second scenario is devices cannot even support HTTPS. So in that case, invoke a Lambda function, right? Which means that you first write a Lambda function, deploy it through AWS IoT Core. And again, same thing. You train a model in Sagemaker, deploy into a production endpoint. So you have a Sagemaker trained model, you have an endpoint, and then you have an you have a Lambda function, which is part of the IoT Core. And the devices which cannot communicate using HTTP, they can communicate using MQTT protocol. So they collect the data, they use MQTT as a transport to AWS IoT Core, and IoT Core triggers the Lambda function, which will invoke the inference endpoint and produce the results. So here, network is available. So obviously, network should be there. But the only difference is, in the former, we made a HTTPS call. Here, we are making an MQTT as a protocol. And as you know, that it's less demanding, right? And obviously, the limitations are, or the requirements are, it has to be provisioned using IoT Core. So again, we can discuss a lot about how we can leverage AWS services for machine learning at the edge. But since we have exactly 30 minutes, I'm going to stop my presentation, and we can switch to a panel discussion. So before I do that, let me stop sharing my screen so that I can see you guys. Can you see my screen? Can you still see my screen?
Yeah.
No, we can't.
No, we can't.
Can you just wait for 1 second? So while I'm doing something, why don't we start with an introduction where you can start with a quick introduction, talk about yourself, your background, your company's vision, and how you're working with Capital Factory. So can we start with JD?
Sure. Is there any slides or not? I just wanted to make sure. If not, just verbal's fine. Okay. So JD Stanley, I was close to 20 years at Cisco. A friend of mine asked me to leave. He was on his 3rd gen product platform. And so we actually are a company that's got a really kind of awesome name. You can see it. It's IoT AI, right in the middle of all the hype. We actually grabbed the domain also of IoT.ai, and I have to laugh because I ran lots of different engineering teams, product teams, sales teams, all on this topic for close to 20 years. And so to leave Cisco and get a name and a brand and a domain of that, it's just kind of funny. But at the end of the day, I also have a black box. And so our black box is at the edge. We have been awarded over $5 million in government contracts in the last 16 months. And so we do everything from a communication and sensor environment to distributed analytics. We're also a finalist with AppWorks on JADC2, the MDO type of environment. And so we specialize as sensor experts, communication experts, and the easiest way to describe it is Extreme IoT. And so at the end of the day, our company has been about almost 2 years old, not quite, driving the innovations we've had from our past into solutions that actually solve the extreme edge, austere edge, mission side, things around maintenance and training, kind of optimizing those business cases. And then we have subcomponents that help in cloud. We actually have some of our components that do run on AWS. We have some components that actually, through a contract with DHA and JHARM, that run on Platform 1 that was talked about earlier today. And then we also have edge components that are really built for really harsh, extreme, really disconnected environments. So it gives you a little bit of background about who we are and what we do.
Thanks, JD. James?
Yeah, how is everybody? So I do want to start out by just saying, thank you to AWS, thank you to Capital Factory. A company like Parasanti, a defense startup would not have been a thing 10 years ago, right? Without the advent of cloud and without the cheaper compute and without the exposure to, the government functions that Capital Factory provides. But a little bit about Parasanti is we are the blue collar analytics company. We're geared towards delivering analytics and machine learning to those who've never had it before, right? And really the focus is on IoT, and the focus is on the warfighter, and the focus is on the farmer in the field, right? What we really focus on is the whole data management aspect and how you utilize all of this information at the edge to make tactical decisions in real time to the people who really need it most, whose lives are on the line, right? So my co-founder and myself are former chief architects for the DoD under Hewlett Packard Enterprise. I've got the hairline to prove it for years of architecting DoD systems. But we noticed a real disconnect from the decision making or data sharing that was happening in Stratcom and happening, in the war rooms around the world, and what was actually happening on the battlefield, right? The collecting of all the Internet of Battlefield things, device information from vehicles to wearables to sensors to virtually anything else, and presenting that information or those insights to the people while they are in theater or while they are actually performing a mission. So that's what Parasanti is all about. You see the thing back here, anti-big data, because we do focus on small amounts of data coming from millions of different devices that are interconnected across the enterprise and across the battlefield. So thank you.
Thanks, James. So probably during our course of discussion, we can talk more about it, but I'm super excited that you're helping the command and control to provide operational intelligence in a kind of a zero bandwidth environment, right? But we can discuss more about it the next question.
Definitely.
Rajesh?
Yeah, good afternoon, everyone. So Edge Tensor, what we focus on is, our mission is to make AI affordable and accessible to the mass market. When I say that, it means that we have developed a very optimized edge AI engine that works on commodity hardware. As I said, we were talking about Raspberry Pi and all of these devices when Wilfred was sharing his slides. So we focus on those kind of devices, and we have built the entire inference engine from scratch in-house, which gives us a lot of leverage. And all the discussions that we had about how to handle the inference, how to handle the data, the memory, the compute, and all of that is basically what we focus on. And then we have built an API that can be deployed on multiple types of architecture, cross platforms, basically, I think the biggest advantage for us is, since we are building it, and we don't have any open source dependencies in our SDK, so that gives us a lot of advantage to deploy it on sub 5 watt devices. And we're also looking into like ultra low power devices, solar powered, and all of that, where quantization, sort of binarization sort of techniques help quite a bit. And from there, of course, we have the entire end-to-end pipeline, the front end, back end, where, because all of the compute that happens on the edge needs to be aggregated on the back end. So we do provide an end-to-end framework where we have video intelligence and analytics, basically the verticals that we work in is mobility. I think one thing that we touched, will test on in the slides, was autonomous vehicles, and we work in that space in mobility for doing distracted driver monitoring, and it's all camera based. So basically, all our applications is driven by real-time camera-based inference. So that's one of the highest sort of consumer of data, bandwidth, and power. So And then the two other application areas that we're looking into are video security and retail. And then of course there is branches of that like smart health or smart cities and all of that. And we do have NSF ongoing grant with the local university here, where we are developing the next generation driver monitoring capabilities for the tech, focused on military vehicles and fighter aircraft and assessment platform and stuff like that.
Very good. Thanks, Rajesh. One thing that was really interesting was your solar-powered devices. So maybe we can discuss about it in the next couple of rounds, right? The questions, right? So which means that I'm assuming that you're not only doing software, you're also building hardware, or you might be having some kind of agreement with the hardware provider. We can discuss that later. So JD, coming back, sorry about it. I did some research on James and Rajesh, but I didn't do a lot of research on IoT AI. So I understand, right? But I'm assuming that the use case is going to be predictive maintenance using a rugged device, as well as a couple of other things, right? So can you elaborate on what is a high-level use case, couple of use cases, high-level architecture, how you're using devices, how you're collecting and analyzing data? And I'm not sure whether you're using machine learning, so if you can elaborate on that, that would be fantastic.
Yeah, we have more recent ones, but I'll give you one that describes a lot of what you just mentioned that ties to actually some of our current projects. But a couple of years ago, we actually, about a little over 18 months ago, the Air Force spends about $1.6 billion on hearing loss and health issues related to a lot of noise and those types of things. We've seen lots of issues that the Army itself has faced in that. And so we did a study with Air Force Medical where we basically had a noise sensor that we developed, and it was wearable in the soldier that communicated to our little device that allowed us to have multi-kilometer communications over RF. Inside of both those devices, we had micro kind of machine learning, parsing actual analysis of the noise patterns that were coming. And then we actually tied that back over a cellular network at the time, but we could have done it over a tactical also because we were doing telemedicine. Back to our cloud component, we have an asset that we call collaborate.org. It's a public site out there everybody can look at. It does have an ADS kind of background, AWS type of a background, but that's a multimodal, multi-stakeholder, multi-data set, open API, ability to share actually cross sectors. Some of the government and actually private sector are using it for COVID-19 right now. And so what we had in that back end was also some deeper analysis where we did genome analysis of Air Force medical records and identified that there are certain genes that actually give people proclivity to hearing loss. And so we actually took what our learning in the big analytic cloud, transposed that down to those micro machine learning modules, and allowed us then to actually look for giving them a warning light, in essence, of saying, hey, your decimal point based off your profile is getting too high. Here's what you're going to do. And so that gives you an example that we use just some hardware we have developed. That's A2AD, very resistant, mil-spec, but also COTS-based. Very lightweight, less than 2 pounds, very low power usage. And then we also tied that to the sensors so we could compute locally in a disconnect. But then we also integrated kind of that edge to cloud to edge loop to ensure that the model locally and in the cloud continue to learn off each other. So that gives you a little bit of background of a use case that kind of relates to a lot of the topics you mentioned.
Awesome, Jerry. That sounds interesting because that clarified one point. You're not only using the devices to collect data to push it back to the cloud where you can do a lot of analysis and predict hearing loss or genome sequencing, but also you're pushing back data to the device, and it also does some kind of machine learning at the edge, at the device itself.
Yeah, no, so a lot of where the market's going and where Amazon, I think, is going, where it's going, and Microsoft, and even Platform One, and what the Capital Factory and also my peers are going, is the nature of the classic client-server model of the cloud works, but when you get to these extreme edges, just like what James was talking about, it's really hard. They don't have power, they don't have connectivity. You are disparate. The mission is actually under constant attack by foreign nations. And it doesn't matter if it's a peer nation or near peer nation, there's constant interference. And so we've actually been optimizing to figure out how to do those things. And that requires the pushing of kind of these micro MLs that are parsed, distributed, closer to that edge, but then still have kind of the big brother or the mother back home that says, hey, I've learned something new from the other children.
So that push back.
Are you seeing something similar or not? And that's really where the evolution is going, kind of that symbiotic cloud to edge, edge back. But also what's been talked about the last couple of days with the Capital Factory and the Fed Supernova is there is a disconnect moment. And that is a missing gap in the market. And so we, along with my peers, we're all trying to address that as the startups across the military environment.
Very good, JD. Over to James. I understand, right?
Yeah.
It's all about command and control, but how do you handle intermittent connections, how you collect data, and how you handle the challenge of sending the data back upstream when you have limited connectivity? And if you can throw some light on it, that would be
Yeah. Well, you know, JD hit the nail on the head, right? You're going to lose connections, and the market we function in, the DoD, is going to lose connections a little more often than everybody else, right? Doing IoT and Industry 4.0 in the middle of Chicago, right, is a lot easier than doing it in the middle of Fallujah, right? So everything about it has to be architected for that environment. So what we do is we have, we talked a little bit about Snowcone earlier. We have our NVIDIA-based GPU devices, right, that can be kind of strung together in a tactical mesh, so we can self-correct our environment in the field, right? So we have a fog network to be operated and to do these machine learning insights and generate solutions to problems with, right? So that functions as one of the problems, right, of us having connectivity to compute. The other major problem is how do we actually use this to operate on the different functions across the C2 environment, right? Yep. So what we do is we actually, and it's kind of similar to what JD's talking about. You kind of have micro machine learning algorithms, right, that perform one single function. But what we do is we have what we call federated machine learning, and it was coined for really keyboards, right, on your cell phone. So you have a local model that's being generated by your typing, and then it sends the insights of that model to the mothership, right, for the aggregate model across the nodes, right? Yep. So we do that same sort of thing with the in-flight, in-theater analytics or data sources that are being generated, and the added benefit is we can utilize those long-range networks because now all that we're sending across the wire is the insights. We're only sending the standard deviations, outliers, and means across the network, and we can communicate in much wider band communications for in-field analytics and C2 operations, right? So,
great, James. Right, you talked about a lot of technical details, but that is awesome, right? I kind of get it within 5 minutes, but I can do more research on that. Yep. But what is the use case you're trying to solve, right? How you're trying to provide operational intelligence when certain people are deployed in the battlefield?
Yep. So what C2 means to us is, command and control. Take all those data sources that are siloed and in different places, deliver it to the end user to actually make actionable decisions, right? So one of the use cases we love to talk about is, taking the wearables off the warfighter, right? There's no shortage of Fitbit type devices. There's no shortage of blood pressure cuffs, even video, right? Taking all of the insights from that, combining that with the diagnostic information that's being put out from the Abrams, right, or being put out from some of the equipment out there. And so a situation we talk about is, hey, this tank driver's blood pressure just has gone through the roof, right? We combine that with the Abrams track vibration going up and the weapons temps going up, and we have the insight of this person's been compromised. This tank's been compromised in some way, shape, or form. Let's send the helo to get them out. Nobody jumps on the comms, right? So that's what we're all about, is saving the warfighter and doing it by connecting all these siloed devices.
Yep.
Right.
Very good. Thanks, James. So Rajesh, I think I went through your website. You made it very clear that it's nothing to do with the cloud. You do everything at the edge, and you have proprietary techniques that you have built to optimize and stuff like that. But I think your solution falls under two broad categories, right? One is mobility solutions, and video processing and security. A lot of people
Right.
do that. Are you thinking about using a service like DeepLens, or are you using Raspberry Pi, or just what kind of devices that you're using for your rugged device, and how you're collecting data and how you're analyzing data? And tell me at least one use case. Yeah.
Yeah, so let me take the mobility use case. What we do in for mobility is, as I said, distracted driver monitoring. So we monitor. There's a camera sitting in the vehicle, like you can think about it as a dash cam, and it looks at the driver, alerts him when he's drowsing, distracted, fatigued, playing with his phone, or eating, drinking, doing anything that he's not supposed to do other than driving.
Yes.
Here it's again, you get devices that we get customers are like, okay, 90% of the time it's always like, okay, I have this 4-core device. What, I have 3 cores that are already occupied by something else. We have 1 core left. Can you fit your AI SDK on that 1 core? So that's the challenge we get in the real world. So basically, how do you take a machine learning in inference engine or AI in inference engine and fit it into single core operation and still be able to do 15 FPS or or more? So that's the challenge that we have. So, and of course the power is limited, the bandwidth is limited, and all of that. So we typically go for, most of our 90%, I would say, is Raspberry like devices that we focus on. And then just to give you on a 50,000 feet level idea about how things work. It's mainly the power is drawn. If you look at any ML architecture, it's all about bringing data from DDR to the cache. So if you are able to optimize your models and also prune your inference engine, well, and again, the thing is, like, if you are in a application where I want to have 10,000 object detection or classification, that's like there's always a model bias there, and you have inequality in the amount of data that you get per class, all of this. So in our case, we have made that kind of we know exactly what we're looking for as an end product, so we can now tune the data according to what we're looking for, especially. So that gives us a significant amount of benefits to quantize the models and optimize the model and fit it into like a sort of a cache-friendly architecture, if you may say, where we make a very 10% round trips to the DDR, and then we can fit everything in just real time, single core, and all of that.
Thanks. I really wish we had another 45 minutes, but we have only 10 minutes. People are pinging me, but still I want to cover a couple of important points, right? So Rajesh, say, for example, I know since you're doing a lot of video processing, I'm thinking that you might be doing a lot of pre-processing of the image, because the device that you're using might capture the whole frame, but you might need only a portion of the image to do your machine learning and so on and so forth. But since I really want to dive deep on multiple things, but we don't have time, but I want to cover at least 2 more things, right? One is security at the edge, right? That is the key thing. We all get it, right? We understand the device constraints, computational constraints, memory constraints, and so on. That's the reason you're doing it. But whatever solution that JD and James and everybody explained, the devices have to connect and exchange information. And in that case, they have to do, especially when you're doing it for a DoD mission, security comes first, right? So I'm just curious how you're handling mutual authentication between devices. Is it based on certificates? How you're doing encryption of the communication, and so on and so forth. So if everybody can spend a couple of minutes on that, I still have one more question that I want to get to. So JD, can you? Yeah, you're on mute.
Yeah. So we actually handle it in multiple different ways, and so our devices are extremely sophisticated to where parts of the defense have actually verified that it's everything from physical to motherboard to kernel to chip to software to actually dual wrapped encryption network. So that entire stack is very resistant.
You're talking about FIPS here.
Yes, so there's a whole bunch of different techniques, but the stack is there. We support over 4,000 different type of sensors natively today. But there are actual different types of sensors, biochem through to IoT vibration. We have some industrial customers, industrial control systems. And so because we support those type of native analog and also digital signals, we actually have multiple levels of attributes that are also keyed when I was at Cisco, I actually worked on how to drift AI systems. Some of my teams were doing that, and so that was my final couple of years there. And so we know a lot about the risk of drifting AI, the risk of human assumptions in AI, and so we've actually countered some of that in our system. But in general, we also are very open to the actual RF networks, the encryption models, and so we have trusted forms that allows us to communicate up through other tactical environments or satellites, commercial satellites, 5G, 4G. But we also have zero trust models that also allow us to do that. And so the level of sophistication isn't just a software level. It actually is from the physical up through to the network, and then the data, and even some of the ML. We have signature analysis of ML to ensure drift analysis, to make sure some of that stuff isn't occurring that can occur through malicious techniques. And so there's a lot of details to that, but it gives you a sense of how we've tried to address the edge, which is very unsecure in a lot of cases, and very multi-party based, to where we support third-party AI, like, for example, or Jessa stuff would probably work on our types of devices. And we also support third-party sensors. And then we also support third-party data exchanges, because everything has to be heterogeneous. There is no forklift upgrades in this environment. And so you have to be able to interoperate. And so we do support all the security protocols, but we've added in some of our secret sauce to kind of help ensure security at those kind of extreme environments that you don't have complete control of. There's a lot of uncontrollable brinkmanship that occurs at the edge.
Yep. Awesome. Thanks, JD. James?
Yeah, so we could probably have a whole nother hour conversation on security at the edge, right? So, you know, how we handle it is everything we have is fully encrypted at rest and in flight, right? We have containerized platforms or everything's containerized, so everything is segregated, right, from the other users on the platform. We also enable a lot of DevSecOps processes, right, to where everything is tested before it's built and before it's actually pushed to the hardware devices itself. And then kind of, you know, going back to our federated model, right, we do have, it makes it so we're distributing the insights across the network. So no one node actually has all of the raw data, and no one node has all of the insights, right? So everything is kind of separated in that way, and that if you do compromise a node and you do somehow get through multiple levels of encryption, you're not really getting the entire picture of what's going on, right? So,
thank you, James. Rajesh?
Yeah, so we use a combination of keys and encryption, and then of course there's a two-level authentication that happens on the device. And with respect to software, there is license encryption and you know, keys that we use to you know, handle all of these at the edge. So you know, and since we are not in military, I think there are some you know, some things that we need to, you know, consider as well. And I think what you guys presented looks very interesting to me. I just wanted to mention also about your cross-platform deployment, which is always a concern for us, because there is no manpower. You can do that in a finite time. It takes a lot of bandwidth from a startup. So I think Sagemaker Neo kind of application is quite relevant for startup like us.
Thanks, Rajesh. So we have exactly 3 minutes, so I'm just going to give you 1 minute each. So this is where I'm strong. Definitely, I'm going to connect with each one of you individually, because I strongly believe, based on the use cases that you presented, there is a scope for, in a selfish way, we can think about Sagemaker Neo for one, an IoT core for encryption and security, right? But having said that, any last thoughts around best practices, lessons learned, and probably each one of you can take a minute, and we can close the session with that. Over to JD. You're on mute.
Yeah, the market's full of hype. We all use the same language, which is hard, right? And so ultimately, what's good is that what Capital Factory's done to put this together and to see what AWS is doing. And so a lot of this is interoperability. And so you will always have a bigger back-end connection for startups and a global scale. And that's something we have leveraged. And so my word of advice to any startup is to consider how you can leverage this in your early days of a startup, because it does help you scale. And then also for the mission side is that we all have a passion for it. It's a big problem, and it will only happen through collaboration across the sectors and across the startups to really kind of help drive that. And so I just thank you for being part of this, and thank you for the work and the sponsorship that Deloitte and you and Capital Factory have done today.
Thanks, JD. James?
Yeah, just echoing that same sentiment. We wouldn't be here without AWS. A lot of the testing and building and every part of our solution is based around what AWS has been able to give to us. And we appreciate the platform and the opportunity to speak today. So thank you.
Thanks, James. Ajay?
Yeah, I think I second JD as well, and thanks Wilfred, and thanks AWS and Capital Factory for putting this together.
Yep.
And giving us an opportunity here. And I think more and more scalability is a big issue for us, for any startup, I think, in early stages. So you can do number of POCs, and beyond that, when you get to like 1 million devices, how do you handle that? How do you do over there updates and things like that? I think if these things we can handle it at an early stage, as JD mentioned, I think that will be a really game changer for startups. And then I hope we can get some help on those lines.
Sure. Thanks again for your thoughts and best practices and lessons learned. And definitely from my perspective, I think we have to dive deeper. I'll connect with each one of you individually and try to find out how we can help you better. Once again, thanks for your time and thanks for using AWS.
Thank you, everyone.
Thank you.
Stay safe and healthy.